To reiterate from last class period, the homework on all the polar coordinate stuff, that's due today at 2, so if you haven't turned that in to me, go ahead and do so now. And I guess the only other thing I mentioned was that the final exam is going to be on the 24th. It will be an in-class test. I am expecting you to be here unless other arrangements are set. So just keep that in mind. Besides for that, I think that is everything that I have in mind. And we can go ahead and start with the new material. So this is a section on inverse circular functions. So looking more in depth at the inverse trigonometric functions, which we have looked at before. We're going to look at evaluations of these inverse trig functions in particular and see how to do so. And so an inverse trigonometric function, there's really two ways you can notate it. This notation is probably the more familiar one for inverse sine, for example. So inverse sine, normally we use this -1 exponent up here, and that normally denotes inverse sine. That's how it's read. There's another way of writing this, and it's arc sine. So if you see the word arc in front of a trig function, that just means the inverse function. They mean the same exact thing, it's just different notation. In fact, you might prefer to use arc sine if, well, I guess since you're taking the final in class, you won't really have to worry about it, but sometimes it's just easier to type out arc sine if you were to, say, take a test and you didn't feel like writing the inverse symbol. It's a little bit messier when you're typing it out. But you will see both of these notations throughout the section, and really we're going to equate them as the same thing. And really what it means for a trig function or an inverse trig function, such as sine inverse of y to be the case, or rather, switch these. Really what this notation means is not necessarily that x will be equal to sine of y, but it means that x is satisfied by sine of y. This goes back to that whole idea of it's misleading to look directly at the inverse trig function because there may be that difference between a reference angle and what the angle actually is, depending on the context. And there's actually a tricky problem in here that really emphasizes that later on in one of these examples. But really, this whole section is going to amount to this table. And so hopefully, yeah, so with this table is going to be given to you on the final. So hopefully you have all seen the note on the right here of the screen. That whole table is going to be given on the final. And I will be referencing this table the whole time throughout the section. And I'll tell you all how to interpret this. So let's go ahead and just look at some problems, and then that'll really start to explain what all of this stuff means. I think that's the easiest way to slowly start to dissect all of this. So let's start with example 1, and we're going to find the exact value of each one of these inverse trigonometric values. Now the interesting part is that the input of an inverse function is not an angle. The input is not an angle. The input is a number, and the output is going to be an angle. And additionally, you're going to find this in your homework. It says we'll find the exact value, which we will find. So if you tried to put sine inverse of square root of 2 in your square root of 2 over 2 in your calculator, what's going to end up popping up you'll get an angle out of it, but you want to make sure that angle, well, one, is formatted in the correct way, and 2 represents the correct angle overall. It does also say, and you will notice this in your homework, real number y. And what real number y means is you want a radian answer. So for all of these, we will produce the final answer as a radian measure when it says real number y. So I believe the first few homework questions find the exact value of each real number y. So we will be providing the radian equivalent. So now what this is saying here, so for part 1 here, for sine inverse of square root of 2 over 2, when it says the real number y, we're assuming that this whole expression equals y. And so we're trying to figure out what y is. And the reason why this is helpful to set it up this way is because we want to find the angle y such that, so if we were to undo that inverse, we would get that sine of y is equal to the square root of 2 over 2. If we were to undo the inverse, which means apply sine on both sides. And the reason why this is helpful is because sine of y is opposite over hypotenuse. We're going to use that momentarily. So that implies a triangle of some sort. But the question is, how do we triangulate? That's where the table comes into play. So what we have is sine inverse. And what this tells us, really the range is less important. The range isn't as important because it's simplified very nicely under quadrants. So it says if the inverse, or if the input of the inverse is positive, we're going to use quadrant 1. And if it's negative, we're going to use quadrant 4. Well, square root of 2 over 2 is positive. So this tells us we will be triangulating in quadrant 1. And so how do we fill in the aspects of the triangle? Well, that's where this part comes into play. The opposite is the square root of 2. The hypotenuse is positive 2. And we could figure out the third side pretty quickly by using the Pythagorean theorem. That's the square root of 2 squared minus square root of 2 squared. And what you're going to end up getting is 4 minus 2, you get the square root of 2. So by filling out the dimensions of the triangle, we now hopefully see what angle that corresponds to. The angle that we get when 2 of the 3 sides of the triangle are the same is 45 degrees. And you do also get this using the calculator. You get the reference angle, which in this case ends up being the, well, this ends up being the angle in quadrant 1 as well. So we can conclude, and of course you have to show your work as well. So using the calculator is just a convenience to help verify your answer. So really, what we get is that y is equal to, let me put this right here. We get that y is equal to 45 degrees, but we need to express the final answer as a radian measure. 45 degrees in radians is pi over 4. And that is your final answer for this one. Using that thought process. you have any questions, maybe hold on to those until after I finish part 2. So with part 2, we have tan inverse of -1. So if we suppose that this equals y, then what we're looking for is the angle y such that if we undo the inverse, we would have tan of y is equal to -1. That's why the symbolism of y is important. So we have this placeholder variable. So now this brings us to solve this. Well, we had tan inverse of -1. So tan inverse brings us to this row. And we have a negative input, which means negative input, use quadrant 4. So when we make the triangle, we're going to triangulate in quadrant 4. Another helpful reason for having tan of y is equal to -1, well, this tells us, well, tangent is opposite over adjacent. So we can think about this as -1 divided by 1. So if the angle is here, then opposite, well, really, opposite, we're going to put 1 for now, and adjacent is 1. Yeah, so the negative has to correspond to this one, because that's the region that's going in the downward direction, which is a negative direction. And we can use this to pretty quickly figure out the hypotenuse. So the hypotenuse here is equal to the square root of 1 squared plus -1 squared, and you end up getting the square root of 2. But you may have already noticed, what triangle, what kind of special triangle corresponds to when 2 of these sides are the same length? That's a 45-45 special triangle, which immediately tells us by using the dimensions of the triangle that the angle here is 45 degrees. It's a 45-45 triangle. But our final answer is not 45 degrees because that is simply the reference angle. Really, the answer would technically be -45 degrees because we're going down, but we need to convert this to a radian because it does say each real number y. So it is expected to write this as negative what ends up being pi/4.
It's like you don't have to like put it in the first quadrant, just use a negative.
Well, we want to stay in the 4th quadrant because that's where the inverse lies. And so that's why, well, maybe you might be asking the same question. Let me know if this is the way you're asking it. Do we have to rewrite -45 using a coterminal angle? And the answer is not really. We don't have to convert that to a positive angle value because it doesn't ask us to. So why not? We can just keep it here. So really your final answer, after it's all organized, said and done, is that y is equal to -pi/4. If you convert it to its coterminal equivalents, which would just be 360 minus 45, so 315 degrees, and then whatever that is in radians, maybe like 7pi/4 or something. That's not wrong. So you can do that as well, but the back of the book will keep the negative value if you check your answers in the back, because they don't really specify that the angle needs to be in a certain range. So now I ask if anyone has any questions before we move on to part 3. Not, let's see if I can try to show the table with the problem. All right, cool. So we'll move on to part 3, which says that arc cosecant, as it's read, of, we're trying to figure out the exact value of arc cosecant of -2 over square root of 3, which is the same exact thing as cosecant inverse of -2 over square root of 3. And really, I convert it to the inverse just because, well, it matches up with our table. Our table up here doesn't have arc, the wording of arc, but if you can make that distinction, then that should be fine. But it brings us to this row right here. Which means we're ultimately going to be using one of these, either quadrant 1 or quadrant 4, which you might notice very quickly, because the input is negative, we're going to ultimately be in quadrant 4. Now, what exactly is happening in quadrant 4? Well, what's happening is that cosecant of y is equal to -2 over the square root of 3 when we undo the inverse. And the only reason we undo the inverse is because now we can see that cosecant is, so cosecant is 1 over sine. So that means this is hypotenuse over opposite. So now we can construct a triangle. And our table above tells us that we will be in quadrant 4 because that input was negative. That's why I'm going to draw an angle in quadrant 4. Now we know that 2 is the hypotenuse and square root of 3 is opposite. And then the negative sign would have to go to the square root of 3. It can't go to the 2 because hypotenuse can never be a negative quantity. That's why the negative square root of 3 is, or square root of 3 is negative, because we're going downwards, which is a negative direction. And if you use the Pythagorean's theorem to figure out the missing length, or the missing side rather, we get 2 squared minus negative square root of 3, quantity squared. Really, you get 4 minus 3, which is 1. You actually just get 1. So hopefully you recognize this triangle here. It's a 1 square root of 3, 2 triangle. That's a 30, 60, 90 triangle. And in particular, we need to figure out what angle corresponds to an opposite of the square root of 3. That one was 60. That one's 60 degrees. But we don't want to use positive 60 though, because that puts us in quadrant 1. Yeah, it's going to be negative pi over 3. So you would think y is negative 60 degrees, but then you remember we have to put the final answer as a radian. which is why we'll just go ahead and convert 60 degrees to negative pi over 3 radians, and then that would be the final answer here. So finally, for arc cosine of -1, that's the same thing as cosine inverse of -1, which we can set that equal to y. We can go ahead and use this information to determine which quadrant we will be drawing the triangle in. Since the input is -1, which is a negative number, so let's see, cosine inverse puts us in this row, which means we're either going to be in quadrants 1 or 2. And since the input is a -1, we're going to be using quadrant 2. That's how you interpret this table. So in fact, I'll even write that on this top line here, just as a reminder. And by setting up the symbolism such, just like this, we can undo the inverse to see that the trig function that we have is cosine of y is equal to -1. Now I'm going to write this out first. That I'm going to write this in red, so don't write this down unless you want to, because I'm going to end up erasing this. So let's say you start going through the motions that, all right, you see that you're in quadrant 2. So you draw your XY plane, and you start to draw your triangle, and you triangulate, and cosine being -1, that tells you adjacent over hypotenuse is a -1 over 1. Adjacent would be down here, and your hypotenuse would be up here. What would your missing side be, is the question. And if you, again, all the stuff in red, don't write this down. If you were to solve for your missing side, it would be 1 squared minus -1 squared, and the square root of that, which is 0. So you get a side length of 0, which doesn't make any sense. You cannot have a side length of 0 unless you are dealing with complex analysis, which we don't talk about in this class. So what does that mean? What does that tell us when we have this, this triangle that doesn't make any sense? It means that the angle that we're dealing with is a quadrantal. That's what that means. And quadrantals cannot be found using triangulation, hence why they have a special name. So that if you chose to write this down, you could just put a big X through it. I'm going to go ahead and erase all of it. So what we found out is that this was, in fact, a quadrantal the whole time. So since it's a quadrantal, we need to remember those x, y, and r formulas. Remember, cosine was x divided by r. And since we have quadrantals, we need to remember. So what we found was that we have to use quadrant 2 here. But quadrantals do not lie in any quadrant. They are the boundaries for the quadrants. So really, we want to consider, in fact, I'll draw this in red, the points for which the second quadrant is limited by. Remember, this point was 0, 1, and this point down here is -1, 0. So which one of those contributes to a cosine of -1? It's the bottom one here. It's the one that obviously has a negative. So really, our angle that we found is a quadrantal that corresponds to 180 degrees. So here, y is equal to 180 degrees because it's a quadrantal. And we found that it is the quadrantal that corresponds to 180 degrees. But we want radians, so really this is just pi, because that's what 180 degrees is in radians. So does anyone have any questions before we move on? Not, let's go ahead and do exactly that. Example 2, so here, well, this seems pretty easy. Use the calculator. Okay, is it really that simple? As long as you do everything in accordance to what it's asking for. So you might notice on your calculator, on any calculator you have, whether it's this one or the TI-80 whatever calculators, the brick sized calculator, you will notice these inverse buttons, and we've used them before, I think. So we've used these inverse buttons before, and they're going to come into play here as well. The only thing you want to keep in mind is where it says y is in radians. So if you do any of these in the calculator, you want to make sure you are in radian mode. So I'm going to take my calculator, put it in radian mode, and now I'm going to put this in the calculator. If you do not put this in radian mode, you will not get the same answer that I do. It would not be considered correct. So I'm putting in sine inverse of 0.1234. We'll round this to, it doesn't matter, 3 decimal places. 2, 3, oh, I said 3. Actually, I'll do 4. Again, it doesn't matter. So if your calculator is in degree mode, you will not get this answer. If your calculator is in degree mode, you're going to get 7 point something something, which is not correct. So problem 2, or part 2. Put this whole thing in the calculator, where y is in degrees. So it's worth putting your calculator in degree mode. And it's also worth knowing, how do you put an arc sine in the calculator? I don't see arc sine anywhere on this calculator. But that's when you remember, oh yeah, arc sine is just sine inverse. It means the same exact thing. And so that's what you can put in the calculator. And you're probably wondering, did I type it in wrong? Because the calculator's complaining. I got a domain error. You should have gotten a domain error. This is because sine, well, the range of sine is -1 to 1, or the domain of sine inverse is -1 to 1. So you're supposed to get a domain error. So this is undefined. It's just undefined. That's all you have to put if you were in that situation on a homework or on the test. Now part 3, well, this one's a little interesting because inverse cosecant, I don't see that on the calculator. So we have to do a little bit of trickery to get it into a form that is calculator usable, or calculator friendly. So how you can do this, so if you find yourself in this situation, we have to undo the inverse, which means we have to bring the cosecant to the other side without the inverse. That's what it means to undo it. So we get cosecant of y is equal to 1.713. And now we can flip both sides. Because what happens when you flip cosecant? You get sine. So this is the reciprocal of cosecant. You can flip cosecant to get sine, but if you flip one side, you have to flip the other side. So you get 1 divided by 1.713. And then from there, we can apply the inverse on both sides. But the inverse is going to be sine inverse. Now y is equal to sine inverse of 1 divided by 1.713. And that is what you put in your calculator. But you need to make sure your calculator is in degree mode, because it wants the final answer in degrees. So then if you keep this in degree mode, what you get is 35 point, and I'll round it to 3 decimal places, it doesn't matter. 716 degrees. Because it wants degrees and not radians. So that's why my calculator was in degree mode when I did that computation, and you should get 35 point whatever. And then we can look at problem 4, which is pretty much the same issue, except y is in radians. So if you want to go ahead and put your calculator in radian mode, you can go ahead and do that right fast, so you don't forget. But we have the same issue. Secant inverse is not in the calculator. So we have to finagle things a little bit in order to get this into a calculator-friendly form, which means undoing the inverse. So now secant of y is equal to 1.41. And then flipping or reciprocating both sides, because the reciprocal of secant is cosine. But if we flip one side, we have to flip the other side. And from here, we reapply the inverse, but now the inverse, instead of secant inverse, it's cosine inverse. So y is cosine inverse of 1 divided by 1.41. And remember, this should be in radian mode, so your calculator should be in radians. And cosine inverse is something you can put in the calculator. I get 0.7824. Again, it doesn't matter. It looks like in the homework, it says it'll be split between decimal degrees, as they call it, which is exactly, well, it's degree form, and you keep it in your decimal, so it's not degrees, minutes, seconds. It's just, you can leave the decimal. Or it'll say, use a calculator to approximate each real number value, which is radian. So keep in mind, it's not going to say y is in radians, y is in degrees. Actually, no, for radians, I lied. It says it right after. It'll say for radians, make sure the calculator's in radian mode. So, all right, I changed my mind. So that's another third of the problems right there. So does anyone have any questions before we engage further? Not? Let's do exactly that. So now the issue, now the question raises to, what about if we have a composition of functions? So maybe from college algebra, you might remember a composition of functions. And this is technically what's going on here right now. We have either a regular trig function within an inverse trig, or swap that, an inverse within a regular, or whatever one I didn't say, that's the other one. So we're going to look at these examples of compositions of trig and inverse trig functions. So what we need to realize is, what is the input? What is the output? What is the output supposed to look like? Is the output going to be a number? So for example, would the output be a number like this, or would it be an angle, or technically a radian mode? So that is something we need to consider. Well, since secant is the outer function, and that means our final answer is going to be a number, as opposed to if the outer function is an inverse, then our final answer is going to be an angle. So let's see what happens. Normally with composition of functions, you start on the inside and you work your way out. So we want to figure out sine inverse of 3 over 5. Let's treat that like it were a problem from the previous page. So sine inverse of 3 over 5 is equal to y. So this is what we did in the last section. This is the same thing as y is equal to, or actually, sorry, not that. Sine of y is equal to 3 over 5. And the reason why it's important to format it that way is because sine is opposite over hypotenuse. So we're going to be drawing a triangle. But the question is, where do we draw the triangle at? And that's where that table comes back into play that we talked about on the first page. We had sine inverse of a positive number. So let's scroll up to the table. So remember, we had sine inverse. So sine inverse of a positive number. The table tells us we will be in quadrant 1 by exactly that reasoning, because we had sine inverse of a positive number. So let's scroll down now that we know that we need to draw our triangle in quadrant 1. And we know that opposite is 3, and the hypotenuse is 5. And you can use Pythagorean's theorem to figure out the missing side, which would be square roots, actually, of 5 squared minus 3 squared. So you're actually going to get 4 from this. And so we get 4 for the missing side. So you might look at this and think, well, that's interesting. How do we figure out the angle? Well, for this problem, we actually don't ever figure out the angle. We don't need to. So what we did for the interior function, for the sine inverse of 3 over 5, we have now determined a triangle that the angle corresponds to. Now we have to find secant. And guess how we find secant? We use the triangle that we just built. So really what we found is a triangle that corresponds to theta. And now this is how the composition of functions works. Now this generalizes to secant. Actually, let me write this in blue because we're pretty much done. So secant of theta, well, this is theta. So secant, hopefully you remember, this is hypotenuse over adjacent. And we have the triangle. Hypotenuse is 5, adjacent is 4. And that's the answer. So we never at any point actually figured out the angle, which I find kind of interesting. So at no point did we need the angle in this. The interior helped us construct a triangle, and from there we use the triangle to determine the exterior function's value. Yeah, so good luck trying to put that in the calculator if you try that. In fact, I'm curious what it comes out to.
It just explodes.
It just explodes. Oh, not too bad. Okay, cool. All right, so that's part 1 here. Let's look at part 2. Sine of sine inverse of 1/2. Now that may look a little funky because I'm very tempted, so don't do this on your paper. I'm very tempted to just cross out sine and sine inverse. But it's not quite that simple. That's misleading. Because we'll find out in part 3. Part 2, it actually ends up being okay, but in part 3, it's not, for reasons you might not see initially. So in part 2, so let's work it out, and it's totality. I cannot say the word anymore. Fully work it out. Okay, that was embarrassing. We're going to fully work it out. All right, so we start off with the interior function. And so we're going to treat that as if it were a problem on the first page. So this says sine inverse of 1/2. Then we're going to set that equal to y, like we did on the previous page. Well, if anything, this puts us in quadrant 1 as per the table. We can already figure that out from this step alone because we have sine inverse of a positive. If we look at the table, actually, anytime we're taking sine inverse of a positive, that's where we end up. Quadrant 1, every single time. So that makes things a little bit easier. So we're taking sine inverse of a positive, and no matter what situation it is, we're in quadrant 1. So
You're never in quadrant 3.
nah, quadrant 3 is not good enough. So we're in quadrant 1, and so now we can undo the inverse because that tells us that sine of y is equal to 1/2, and we know that sine is opposite over hypotenuse. And so we know how to construct this triangle now. We know every aspect of it. We just have to actually do it. So if we construct the triangle in quadrant 1, like it says, we triangulate. Opposite is 1. The hypotenuse is 2. And if we want, we could figure out the missing side as well, which would, by Pythagorean's theorem, this is 2 squared minus 1 squared. So So that's square root of 3. So technically, it's a 45-degree angle, but we don't need the angle because we're just going to turn around and find sine.
Isn't 30-degree angle? That's 30.
Yeah, you're right, 30 degree. Yeah, you're definitely right. It's a 30-degree angle. Yeah, because it's across from 1. All right, cool. Yeah, so technically we could find the angle, but we don't need it because what we did is we found a triangle that corresponds to theta, and we're going to turn right around and figure out sine of theta, which does end up being 1/2, like the initial impression of cancellation would have you to believe.
Or sine of 30, which is just 1/2.
Yeah, sine of 30 degrees, which is 1/2, regardless.
I'm guessing this one doesn't work because it's quadrantal.
Let's look into that one. So, yeah, so part 3, I'm going to put this in red. So what about if this were pi? And what you're saying is that the output of sine inverse is pi. The problem with that is the range. The range of sine inverse does not cover pi. So that dual cancellation would not be accurate because the range of sine inverse does not reach pi. So by saying that, you would instantly contradict the range of the inverse. That's a lot more technical of a way to look at it, but I figured that's a more convincing way than ever. But what about if we just did it using good old trigonometric methods? So in this problem, it is not true that sine inverse and sine cancel, as that does lead to a contradiction in its current form. And also notice for this problem, the inverse and the trig function swapped places. Notice now the inverse is on the outside and the sine is on the inside. So really what we're going to be getting is, if anything, an angle, because the output of an inverse is an angle. Our final answers before were just numbers, but the output of an inverse is an angle, and they tell us to use radian measure, so it's going to be in radians. So if anything, well, you might actually like this problem a little bit better, because the interior asks you to find sine of pi. Hopefully by now you all know sine of pi, and if not, you could throw it in the calculator. Sine of pi is 0. Sine of pi is just 0. So now we have sine inverse, guess what? 0. And now this goes back to a problem from the first page. Now I'm going to write this in red, which normally means that, well, don't write this next part down. So let's just say this is your new problem. Well, no matter what, this is your new problem. And let's say you try to construct the graph like you did before. And you'll end up finding that you're in quadrant 1. So what would this come out to be? This would be, you would set this equal to y, and then you would get that sine of y is equal to 0, which is opposite over hypotenuse. So then your opposite would be 0 and your hypotenuse would be 1. So you have a dimension that's equal to 0, which doesn't make any sense. You cannot have dimensions equal to 0. So it's a quadrantal. So it is, in fact, a quadrantal. This is a quadrantal because you try to do all of the requisite steps and you end up hitting a contradiction with a dimension of your triangle that is equal to 0. So instead, since we figured out that we have a quadrantal, now what we need to do, so it said look at quadrant 1. Well, the quadrantals don't lie in a quadrant, but we can look at the points that surround quadrant 1. So quadrant 1's over here. So we can look at the two axes, or the two angle values that surround quadrant 1. Where one of them is 1, 0, and the other one is 0, 1. We need to figure out which one of these corresponds to sine of y is equal to 0. Or if you could just figure out what angle gives you sine of that angle equal to 0, you could just skip this whole process outright. But this is y divided by r. This is x and that's y. This is x and that's y. So the only one that works here is this one. Because you would have 0 divided by 1. So really, sine inverse of 0 is equal to 0. That's actually your answer right there. So the quadrantals are a little tricky here. So as you can tell, this section brings a lot of theory together. So let's go ahead and look at part 4. And as you all noticed, the sine inverse and the sine did not cancel from the previous problem. So just because sine inverse and sine are right next to each other doesn't mean that they cancel outright to just get pi. As we noticed, final answer was 0 and not pi. So let's look at part 4 then. And so again, the inverse is on the outside and the regular trig function is the interior function. We can go ahead and figure out sine of pi over 2 first, because that's pretty easy. Sine of pi over 2 is 1. So we can already simplify this tan inverse of positive 1, which brings us right back to the set of problems from the beginning of the section. And since we are taking tan inverse of a positive number, I mean, you could use the table or not. Anytime you take tan inverse of a positive, you're going to be drawing a triangle in quadrant 1. So really what we have is that tan of y is equal to 1, which is equal to opposite over adjacent. So when we construct our triangle, and triangulate accordingly, we know how to fill in some of the dimensions of the triangle. In particular, opposite is 1, adjacent is 1, and we can go ahead and use Pythagorean's theorem to figure out the last one, which is going to be square root of 2. Because 1 squared plus 1 squared. Get the square root of 2. It's 45 degrees. Again, actually, yeah, that is helpful to know. We do want to know that. Because the output of this needs to be, yeah, so the output of this needs to be an angle. Yeah, that's right. So here we do need to know the angle because we don't have an exterior trig function to feed off of this triangle. Or in other words, the output of an inverse function is an angle. So tan inverse of 1, we recognize the triangle to be a 45-degree angle, but they want the final answer in radians, which is pi over 4. That's right. So that is the final answer for part 4. So this section brings a lot of various themes together from other sections, as well as example 4. That also brings in something kind of unexpected. You want to ponder what that process may pertain to. Does anyone have any questions about anything we've done up to this point? If not, let's look at the last problem from this section. This just looks kind of strange. Tan of arc sine of something plus arc cosine of something else. So that's actually a little bit interesting here. So really the question is, how do we even start this? So there's no real way to bring this together. There's no way to nicely add inverse functions together, because remember, that's all this is, inverse functions.
So you find them out separately.
We can find them separately. Remember, the answers for these, the answer for this is an angle, and the answer for this is an angle. There's only one problem with that. So let's go ahead and do these off to the side. So I think, or I hope that everyone already sees that we can treat all the arc sine cases, or the arc sine as sine inverse, because it's just a notation thing. Negative 3 over 5. And let's go ahead and do both of these off to the side. I'm going to do sine inverse all the way down here. Then by constructing its triangle, so we are taking sine inverse of a positive number. This does tell us quadrant 1. Anytime your input's positive. So what this tells us is that sine of y is equal to 3 over 5, which is opposite over hypotenuse. So we draw a triangle in quadrant 1. Opposite is 3, hypotenuse is 5, and you can quickly determine that the adjacent value is 4 using Pythagorean theorem. Or in other words, it's a 3, 4, 5 triangle. Now the problem lies, if you were to try to find the angle of this, it's not going to be nice looking.
And then you can't use tan because it's plus cosine.
That's right. And it says exact, so you can't just throw this in the calculator and try to bullshit your way using decimals. I'm not going to take that answer. So that's the problem here. But there is another way. This gives you an angle. Let's call that angle A. This gives you an angle. Let's call that B. So off to the side, we realize this is tan of a plus b. But wait a minute, I've seen this before. That's the sum formula for tangent. That is the sum formula for tangent. We have a formula for this scattered somewhere in this conglomeration of trigonometric notes that we have here. And if you need a refresher, this is tan of A plus tan of B. In fact, I don't even have enough room to write this. Maybe I'll write it off on the left-hand side. So this is off to the side. Tan of A plus B is equal to tan of A plus tan of B divided by 1 minus tan of A times tan of B. So if we were to apply this formula to our current problem, it tells us that we would have tan of A, which is sine inverse of 3 over 5. Well, in fact, I missed my chance to really write this in a lot more compact way. Actually, I did. I changed my mind. So this is tan of A plus tan of B. In fact, I'm just going to end up rewriting the whole formula, which is fine. Because what we're doing here, in fact, I'm going to, okay, it works out perfectly, actually. I'm going to erase all of this because as long as we are careful with our labeling, then what we have done is we have constructed angle A over here, and we can construct angle B over here, which would be the cosine inverse of, the cosine inverse stuff. So we could do, nope, not sine, cosine. Cosine inverse of negative 3 over 5 is equal to y. Cosine inverse has a negative input, so we need to use the table to figure out what that corresponds to. So cosine inverse has a negative input, which means we use quadrant 2, as per the table, the table's request. So we're going to be in quadrant 2. So in other words, cosine of y is equal to negative 3 over 5, which is adjacent over hypotenuse. Let me draw this with respect to quadrant 2, which will have most of the action here. So quadrant 2 is where we will draw the angle. We will triangulate accordingly. Adjacent is negative 3. Makes sense because we're going to the left. Hypotenuse is 5, and you will figure out that opposite is 4. So we drew angle A off to the left, angle B off to the right, and now we just have to figure out tangent of all of those. And actually, I'm going to write those in red. I'll just have them quickly available. Tangent of A, tangent's opposite over adjacent, that's 3 over 4. And over here, tangent of B is equal to negative 4 over 3. It's 4 divided by negative 3. negative 4 over 3. So really, that tells us exactly how to plug everything in. Tan of A, that's 3 over 4, plus tan of B, that's negative 4 over 3, divided by 1 minus 3 over 4 times negative 4 over 3. Let's see how this comes out as a final answer. Oops. 3 over 4, negative 4 over 3. Negative 7 over 24. It's like a 3-part problem. So let me check something. 6, 8. Okay. Does anyone have any questions about this? If not, this homework, I'd like for this to be due Tuesday. I'd like for this homework to be due next Tuesday. I am going to take off 89, because there's too many of those. I'm going to take off 89. These are all calculator problems, so they should be a little bit quicker to do. 17, 24, 28. So all of those are finding the final answer in radians, and then 38, 39, and 46. These all want your answer in degrees. 51, 54, and 67 are all calculator, and then 60 or 76 and 78 are like the last ones we get. So you could follow this in order of, maybe not an exact order, but that's pretty much the partition between each collection of problems in this homework. And I did omit 89, so don't do 89. So I guess the question is, should I use the remainder of class time to work out one of these problems? In particular, I bet you would all like to see one of the problems that I just worked out again, but different example. So that's sounding pretty clear to utilize these last 6 or so minutes. So I'm going to do exactly that. Use this last class period to be generous and do one of these problems. Presumably one of these last ones. All right, so which one do I want to do? Wait a minute, I omitted the wrong one. I want 89 back. I want to take out either 76 or 78. Let's see. Take out 76. All right, so I changed my mind. 78 and 89. Okay. So take out 76. I'm bringing back 89. 76 is the one I omitted. All right, so I guess I'll do 89. Guess I'll do the one I just brought back. And this is on page 265 in the book. Remember, this is section 6.1 in the book. And what this says is sine of sine inverse of 1/2 plus tan inverse -3. It's a problem just like the one we just did, where we're going to call this one A. We'll call this one B. We're going to figure out both of their triangles. And by doing that, we can utilize the addition formula for sine of A plus B, which is sine of A, sine of B. Oh, wait, no, that's not it. Sine of A cosine of B plus cosine of A sine of B. Pretty sure that's it. If that's not, just remind me. I can't remember. We're going to do the same process no matter what, the same beginning process. So if someone figures it out, just let me know. So down here at the bottom, we're going to do angle A over here. We'll do angle B over here. So since we have sine inverse of 1/2, set that equal to y. The input is a positive number, which always puts us in quadrant 1. So really what this is telling us is that sine of y is equal to 1/2, which is opposite over hypotenuse. So by using triangulation in quadrant 1, opposite is 1, hypotenuse is 2. You can use Pythagorean's theorem to quickly figure out that the missing side length is the square root of 3. Two squared minus 1 squared is square root of 3. And we can do something very similar for angle B, because now we filled in all the dimensions of the A angle. B angle, we can do the same exact thing. B says that tangent inverse of -3, we'll set that equal to y. When is tan inverse negative? What quadrant does that put us in? Tan inverse is negative in quadrant 4, according to the table. Quadrant 4. So in other words, tangent of y is equal to -3. And I'll put divided by 1 because this is opposite over adjacent. So we are in quadrant 4. Opposite is -3, adjacent is 1. And we can quickly go ahead and figure out that the hypotenuse is 1 squared plus -3 squared, but we have to take the square root of that. So this is really square root of 10. So now we need to figure out sine of A, cosine of B, cosine of A, and sine of B. So really, we are going to be doing these for, well, for each one of these angles. So sine of A, we look at the A triangle, and that tells us 1 over 2. So sine of A, according to this triangle, is 1 over 2. We will need cosine of A, which seems to be square root of 3 over 2. We'll write that down in a bit. Sine of B, according to this triangle, is negative 3 over the square root of 10. Cosine of B seems to be 1 over the square root of 10. So now we can just fill in directly. And I'm out of time, so I'm going to hurry up and write this down. Cosine of A is root 3 over 2. Sine of B is negative 3 over the square root of 10. So what is that? That's 1 over 2 square root of 10 minus 3 root 3 over 2 square root of 10. 1 minus 3 root 3, they already have the same denominator, 2 root 10. Cool. Final answer. Whenever you're done writing, you're good to go. I'll go back